Hi, welcome back to another episode of Algebra in Words, the video series on YouTube. In this episode, we're continuing our conversation from the last videos of absolute value equations, and we're also sort of adding on to inequalities that we discussed in previous videos as well, combined to make absolute value inequalities, which I did not write on the board, but I'm going to do. There we go, absolute value inequalities. Now, by the way, if you want to follow along in written form of what we're about to go over today, you could follow along with it in written form in my book, Algebra in Words 2, starting on page 25, which you can find on Amazon, and the link to that is in the description box below. So anyway, let's get started. Now, first of all, what is an absolute value inequality? Well, basically, it's an inequality statement, like any inequality statement. It's got an inequality symbol in it, like that or like that. And it's also got an absolute value group in it, like this and like this. They're the same. But what's more important is now to shift a little bit into the graphical representation so that you can get a more conceptual understanding of what's going on. So what I have on the board here is a graph of an absolute value graph. Now, this hopefully will all make sense when you can see how this all fits together. A lot of books, it seems, do not seem to explain it as clearly as I think I'm going to. Now, first of all, let's focus on the blue graph, which is strictly this part, the absolute value group. So let's say that we had f of x is equal to 2x plus 1, and we just graphed that. And how could we graph that? We could make up a table of x values, say of x equals 0, x equals 1, x equals 2, substitute into the absolute value equation, and then get the values and graph the points. So anyway, the absolute value group 2x plus 1 makes this V-shaped graph. Okay, and in terms of absolute value graphs, we always expect an absolute value to make a V-shape because if you think about it, that makes sense because all of the values of y would be positive because everything from an absolute value group is positive. Now that could shift up or down on the graph based on a few different things. I don't go into that in this video, but there could be shifts on the graph where the V could either be higher from the x-axis or lower from the x-axis, or shift left to right, or even flipped upside down. But that's for a separate video. But for now, let's just focus on the blue V-shaped graph that is the result of the absolute value 2x plus 1. Okay, so think of that as one graph. Now on the same graph, let's say that I said to graph the equation for a horizontal line, y equals 1, okay? And don't you agree that would be represented by this line? The red line is the equation y equals 1. Now, if you notice, you probably didn't notice yet, but suppose that we connected them into one equation, basically set one of those equations equal to the other. That's where this comes from. That's why this equals this, and it's really showing, okay, so when we say, so where does it come from when we say the absolute value group 2x plus 1 equals 1? It means their equations equal, but more specifically it means at what points do the graphs of each of those equations overlap. And in short, that would be at this point and at this point. Now what you may not realize is that as we solved in the previous video, when we solved absolute value equations and got two answers, those are the answers that we got. It would have been this or this, relevant of course to its own equation. It's not going to be the same point on each equation. But again, my point is to reiterate, in the last video when we solved equations like this, absolute value equations, the two answers that we got are the points where the V graph crosses with the horizontal line graph. And now that graph relates to absolute value inequalities as well. I have two inequalities, absolute value inequalities here and here. One of them happens to be greater than or equal to 1, and one of them happens to be, this is less than or equal to 1, inclusive. This one is greater than 1, and I chose them specifically. But let's talk about how that fits into and ties into the graph, because I think once you see it and can think of it from a graphical standpoint, it'll make the rest easier, even though we are going to use some non-graphic graph strategies to solve. So basically, let's go back to this horizontal line, y equals 1. That's what this one and this one is. And this v is the absolute value part on the left, graphed. Now, when we say less than or equal to 1, less than, think of below. So specifically, this equation here, which says the absolute value group is less than or equal to 1, what it's asking is, what are all the possible x values, or the domain, of the v graph below or less than the horizontal line y equals 1? If we were, okay, so let me come back to that in a second. But then, now also, before we move on, since this is inclusive, it would include any points that are also on or touching the line. But what about if it said greater than 1? Well, if we go back to the graph, think of greater than or above. This is asking, what are all the x values, or the domain, of the blue v graph, only that are above, non-inclusive, of the graph or the line y equals 1. Okay? So, that being said, I'm sure that gives a lot of clarity to this, but I'm going to write a few things on the board to just give an overview of what we're going to do. What I put on the board are the three methods that you can use to solve an absolute value inequality. One method is graphically, or the graphing method. That's a method that basically we could already do right now, which is you're either given the graph, or you can generate a graph by making up a table of points and graphing it yourself, and then basically looking at the graph and keeping in mind that less than or less than and equal to means the values of x of the graph below the line, or greater than would be the values of x above the line. So that's the graphical method, which you can basically do by either just looking, or you might have to make the graph yourself and then look. I'll leave the graph on the board, and we'll do each of the other two methods and then compare the answers at the end, which will come out to be the same. The first method, again, is the graphical method. The second method I call the test point method. And I'll explain that fully shortly, but also if you're ever used to doing solving what's known as a quadratic inequality, the test point method is basically the same method used for there. It's basically the same. That you can find in my book Algebra in Word on page 104. And then the other method is known as what I call the keep, change, change method. And that's just the name that I gave it myself, but it pretty much summarizes the procedure, and we're going to look at each of these three methods. So anyway, I'm not going to do the graphing method, but we are going to compare the graph to our second method, which is the test point method. And I'm going to pause the video and show you that next. So I erased some stuff on the board, and just so that you're aware, I made a little change up here. I erased some of this, and I put less than or equal to 1, because that's the absolute value inequality that we're going to solve as our example here using the test point method. Now, before I run through the method, keep in mind that the written procedure is in the book Algebra in Words too, as I said in the beginning of the video, but I'm going to verbally give you a quick little overview of the steps involved. So the first thing that we're going to do is take the inequality and make it an equation. Then we're going to solve the equation like we would as if it was an absolute value equation. And by solving, keep in mind that we expect to get two x values. The x values are what I want to call, for lack of a better term, let's call them border points. We're going to take the x values, or the border points, and we're going to graph them on a number line, just like an x-axis only. And then the border points should split up the number line into three regions: a left region, a middle region, and a right region. And using interval notation, we're simply going to define each region. The next step then is we're going to choose three test points, a test point from each region, keeping in mind that we cannot use a test point that's the same as a border point, because it wouldn't be between, it would be, we can't use a border point as a test point. The way that we test each test point is to take each value and substitute it back into the original inequality, which would be this, and test it, meaning when you substitute the value in and simplify, does the inequality statement make sense? If it does make sense, then we keep the region that we're testing as part of the solution. But if it fails the test point, then we reject that region as part of the region of the solution. And that's pretty much it, but then in the last step, it depends on the form that you want to report your answer in. I would say interval notation, that's probably good enough. So anyway, let's get started. And you can replay what I just said and use it to walk yourself through a problem if you're doing homework. You can also use what we're about to do to walk yourself through a problem as well. The first step is to take what's at the top and make it an equation. So change the inequality symbol to equals. And I'm just going to rewrite it new. So 2x plus 1 equals 1. And if you need a review on how to solve an absolute value equation, which is what this is now, you can watch one of the previous videos, but we're going to do it now anyway. So basically, we're going to split this up into a positive and a negative. So let's do the positive here. 2x plus 1 equals, and the positive of the 1 is just going to stay 1. And let's solve that all the way through. Minus 1, 2x equals 0. Divide both sides by 2. And 0 divided by 2 is 0. So the first point that we get is x equals 0. I'm going to circle that, but actually, let me just put this off to the side so we have room to do the next one. Okay, and I'll pause this and erase it. And now let's solve the top equation for the negative form of the equation. Keeping the front part the same, removing the absolute value bars. And the negative refers to what's on the right. We're going to now make the 1 negative 1. And now we're going to solve for x. Minus 1, 2x equals negative 2. On the right, divide both sides by coefficient 2. And negative 2 over 2 is negative 1. So we get x equals negative 1. And again, just to save room, I'm going to move this over here with that 1. And so we have x equals 0 and x equals negative 1. That's kind of the first or second step of the problem. And I erased that work just so we have more room to work here, but if you need to see it, you can go back. Now, let's pause for a second and just kind of notice something. We solved the equation and we got 0 and negative 1. And if you remember, what is solving an absolute value equation? It's where the lines cross. So 0, x equals 0, and x equals negative 1 makes sense here. But that's just a little aside. Let's continue with the procedure. And the next step is to make a number line these that we just solved for are going to be border points, and we're going to plot the border points on the number line. So let's draw the number line here. And we're going to have -1 and 0. And that's plotting the border points. So that step is done. The next step is to notice that we have, I drew dotted lines just to make it clear that we now have 3 regions, a left, a middle, and a right. And using interval notation, we're going to define each region. The left region is going to be -infinity and -1. And because this is an inclusive symbol, we're going to make that a bracket. Now let's define the middle region. Again, this is inclusive, so we're going to use bracket, -1, 0, and a closed bracket. And now let's define the region on the right. Open bracket, 0, comma, infinity with ending with a parenthesis. So that step is done. We just defined each region based on the border points using interval notation. And now, choose a test point in each region and try to choose the easiest one if possible, like the most simple number. Remember, the only criteria is you cannot choose a border point as a test point. So we cannot use -1 or 0. So let's look in the left region and let's use -2. So let's say test -2. And in the middle region, between -1 and 0, we have no choice. We have to use a fraction, so let's use -1/2. And then for the right region, let's use 1. And now we're going to just simply, one at a time, take each test point, substitute it back into the original inequality. Make sure that it's the inequality, not the original equation, but the inequality. That's what's going to allow us to actually test the truth of each statement when we simplify. So let's start with, -2. And fill that into the original inequality. So 2 times -2 in for x plus 1 is less than or equal to 1. And two times -2 is -4. Plus 1, and I close the group, is less than or equal to -1. -4 plus 1 is -3. Is less than or equal to 1. And now we take the absolute value of -3, which is 3, positive 3. So now if you can see there, we simplified it down as much as possible to 3 is less than or equal to 1. And now we have to check that. Does that make sense? Is that true? Is 3 less than or equal to 1? No, it's not. So we could say no, but what does no mean? It means we reject the region that we're testing. So just to make it clear, I'm just going to put a cross through that region. Now let's test the next one, and I'm going to erase this work so we have room. Okay, and to save a little time, I wrote it out and filled in -1/2 in for x. So let's just simplify. So 2 times -1/2 is going to be -1. And bring down the plus 1. Okay, and now we have inside the bracket, inside the absolute value group, -1 plus 1 is 0. And the 0 has no sign, so when we take the absolute value bars off, it stays 0. and bring down the less than or equal to 1. And now let's read the statement and see if it's true. Is 0 less than or equal to 1? Is that true? And the answer is yes, that's true. Or you could say true. So we now will keep the region that we're testing as part of the final solution. And finally, let's test the last point. And again, I'm going to erase it to make some board room. And again, I wrote the equation and I filled in the 1 for x, and let's continue to simplify. So we have 2 times 1 is 2, plus 1 is less than or equal to 1, and in the left we have absolute value of 3. So let's write absolute value of 3, and then that's going to become 3, positive 3. Bring down the less than or equal to 1, and let's read the final statement. Is 3 less than or equal to 1? Is that true? No, that's false. False or no. And what does that mean? It means we reject the region that we just tested as well. That would be this region, because that's where the test point 1 came from, and so we reject that. The problem is done. Whatever regions defined by interval notation remain is the solution. So this is the solution, and it's done. It's already circled. There's nothing left to do. Let's use this and compare it to the graph to see if it makes sense before we end the video. Remember, this is the original inequality we're testing. The absolute value of 2x plus 1, that's the blue V, is less than or equal to 1, and the 1 is the horizontal red line. Less than or equal to means below the red line, the x values of the blue graph below the red line, including any dots that are on the red line. So if we look here, don't you agree that this is negative 1? Okay, which goes up to here. And don't you agree also that this is 0, because it's here. And so our solution actually makes sense, because only the x values of the blue graph below or less than the red horizontal line 1 are between the region of negative 1 to 0 inclusive. So it could include the points where they touch on the red line. So I hope that makes it clearer for you using the test point method. I'm going to do more examples of the test point method, but also in another video. But also in the next video, we're going to be looking at the keep change method.